Hi everyone, welcome to One Stop Mathematical Solution. Today we are going to solve CSIR NET December 2012 question paper. In this video we have only dealt with the complex analysis part. First question, question 33. Consider the functions f, g from c to c defined by f of z is equal to e per z, g of z is equal to e per I z. Let s is equal to set of all z in c such that real part of z belongs to minus pi to pi. Then, so we are given two functions here and a set s is defined here. Then we have to check which of the following option is correct. So first of all, we'll look into the concepts used. F from u to v is an onto function if every element in v has a preimage in u such that f of x equal to y. F is a bounded function if there exists an m such that mod f of z is less than or equal to m for every z. So now we'll move on to the question. So they are given f of z equal to e per z, and we know exponential function is always an entire function. But for z equal to 0, there is no preimage in domain C because e per z is never 0. So f cannot be an onto function. Given s is equal to set of all z in C such that real part of z belongs to minus pi to pi. So if I take z equal to x plus iy, we will get x belongs to minus pi to pi. That is, x will be less than or equal to pi. I am applying exponential on both sides. So we'll get e per x is less than or equal to e per pi. And we know e per pi's value is minus 1. That is, e per x is less than or equal to minus 1. So now consider f of z is equal to e per z. To check f of z is bounded, we have to take its modulus value. So mod f of z is equal to e per z, that is equal to e per x plus iy. Now I can split both the terms. So this is equal to modulus e per x into e per iy. Again we can split this modulus value. So this is equal to modulus e per x modulus e per iy. We know modulus e per iy is always 1. So this is equal to modulus e per x, and exponential is always positive. So we can neglect the modulus sign. So this is equal to e per x. And from this, the given set, e per x is less than or equal to minus 1. So this implies e per x is less than or equal to minus 1. That is, mod f of z is less than or equal to minus 1. That is, f of z is bounded on the set S. Now consider g of z is equal to e per iz. To check g of z is bounded, take its modulus value like before what we did. We'll do that. Mod g of z is equal to e per iz. Z is x plus iy. Substitute that. This is equal to modulus e per I into x plus iy. So when we multiply by I, we'll get this is equal to modulus e per ix into e per minus y. So now we can split this modulus sign. So this is equal to modulus e per ix modulus e per minus y. E per ix value is 1. Modulus e per ix value is 1. So this is equal to modulus e per minus y. Exponential is always positive. So we'll neglect the modulus sign, and this is equal to e per minus y. But here y is not bounded by any number. So e per minus y is also not bounded. Therefore, g of z is not bounded on C. So now we'll check the correct option. So the correct option is f is bounded on S, that is third one. Next question, question 34. Let f from d to d be a holomorphic function with f of 0 is equal to 0, where d is the open unit disk set of all z in C such that mod is less than 1. Then, so we are given a holomorphic function f here. So we have to check which of the option is correct. So we look into the concepts used. Schwarz lemma. F is analytic in D equal to set of all z in C such that mod is less than 1. F of 0 is equal to 0 and mod f of z less than 1. Then mod f of z is less than mod z for every z in D. Application of Schwarz lemma. Suppose D is equal to mod z less than 1. F is a function from D to D is an analytic, and f of a is equal to b for some a in D. Then mod f dash of a is less than or equal to 1 minus mod f of a whole square divided by 1 minus mod a square. So now we'll move on to the question. So the question satisfies Schwarz lemma's hypothesis. Therefore, mod f of 1 by 2 is less than or equal to mod 1 by 2. 1 by 2 is a positive quantity, so this implies mod f of 1 by 2 is less than 1 by 2. Also, we'll get from the second concept, mod f dash of 0 is less than or equal to 1 minus mod f of 0 square divided by 1 minus mod 0 square. We have f of 0's value equal to 0. So when we substitute and simplify, we'll get this value as 1. So this implies mod f dash of 0 is less than or equal to 1. So now we'll check the options one by one. First option, mod f dash of 0 is equal to 1. But we got mod f dash of 0's value is less than or equal to 1. So if we take mod f dash of 0's value to be 1 by 4, this option cannot be possible. So this option is not always true. Second one, mod f of 1 by 2 is less than or equal to 1 by 2. So we got mod f of 1 by 2's value is less than 1 by 2. Therefore, for any value, this mod f of 1 by 2 is going to be less than 1 by 2. So this is correct. Third one, mod f of 1 by 2 is less than or equal to 1 by 4. We got mod f of 1 by 2 is less than 1 by 2. But 1 by 2 is greater than 1 by 4. So this option cannot happen. Similarly, 4 cannot happen because we have mod f dash of 0 is less than or equal to 1 and 1 is greater than 1 by 2. So this option also not true. So the correct option is second one. Next question, question 35. Consider the power series sigma n equal to 1 to infinity z power n factorial. The radius of convergence of this series is. So we have given a power series here. We have to find its radius of convergence. So we look into the concepts used. For a power series, sigma n is equal to 0 to infinity, an z minus z0 whole power n. The radius of convergence r is given by 1 by r is equal to limit n tends to infinity modulus an power 1 by n, or you can use 1 by r is equal to limit n tends to infinity modulus an by an plus 1. And note, for a power series sigma n is equal to 0 to infinity z minus z0 whole power n, the radius of convergence r is equal to 1 for any power n. So we'll move on to the question. So they are given the power series sigma n is equal to 1 to infinity z power n factorial. So using the concept 2, we get the radius of convergence of this power series as 1. So now we'll check the correct option. So the correct option is third one. Next question, question 44. A bounded harmonic function in the unit disk centered at origin and taking the value sine 2 theta on the boundary is. So we have to find a function which is bounded harmonic in the given region and satisfying this condition on the boundary. So we will look into the concepts used. Function f is bounded if there exists an m such that mod f of z is less than or equal to m for all z. Harmonic function f of r theta is a function which satisfies Laplace equation. Laplace equation in polar form is FRR plus 1 by r FR plus 1 by r square f theta theta is equal to 0. So now we'll move on to the question. So they are given the region to be unit disk centered at origin, that is mod z less than 1. So if I take a polar coordinate z is equal to r e raised to I theta, then this implies mod r less than 1. And we have to find a function f such that it should be harmonic, bounded, and f of r theta is equal to sine 2 theta on the boundary of this unit disk, which is mod r is equal to 1. So now we'll check the option wise. So first option, f is equal to r square sine theta. So first we'll check whether it is bounded, take its modulus value. So mod f is equal to mod r square sine 2 theta. So now we can split the modulus sign. So this is equal to mod r square into mod sine 2 theta. We know modulus of sine values less than or equal to 1, and we have got mod of r is less than 1. So together we'll get this is less than or equal to 1. So modulus f is less than or equal to 1. Therefore f is a bounded function. Now we'll check whether it is harmonic, that is whether it satisfies Laplace equation in polar form. So find fr, frr and f theta theta. So fr is equal to partially differentiate f with respect to r. So this is equal to 2r sine 2 theta. frr means the second derivative of fr, f with respect to r. So frr is equal to 2 sine 2 theta. F theta means partially differentiate f with theta. So this is equal to 2r square cos theta. F theta theta means second partial derivative of f with respect to theta. So this is equal to minus 4r square sine 2 theta. So now check the Laplace equation. frr plus 1 by r fr plus 1 by r square f theta is equal to 0 or not. So substitute the value. So once you substitute and simplify, I am getting it is equal to 0. Therefore f is harmonic. Also we will get f is equal to sine 2 theta on the boundary mod r is equal to 1. So the option 1 is correct. Similarly check it for second and third option. Now I will show the last option. F is equal to 1 by r square sine 2 theta. So first we will check for bounded condition. Take it modulus value. So mod f is equal to mod 1 by r square sine 2 theta. Now we can split this. So this is equal to 1 by r square mod sine 2 theta. But we got mod r is less than 1. So 1 by mod r will be greater than or equal to 1. And sine theta's value is less than or equal to 1. So together we'll get this is greater than or equal to 1. But this implies f is not bounded. So this option cannot happen. So now we'll check the correct options. So the correct option is first one. Next question, question 79. Which of the following are entire functions and have symbol zeros at z is equal to ik for all k in z? So you have to find which of the following options have symbol zeros at z is equal to ik, and also there should be entire function. So first of all we'll look in the concepts used. Z naught is 0 of f of z if f of z naught is equal to 0. So now we'll move on to the question and we'll look option wise. So first option is a polynomial function. So polynomial function is always entire. So now we'll check whether ik is in symbol pool. So f of z is equal to an z power n plus an minus 1 z power n minus 1 plus etc. up to a naught. So from this I am taking z power n outside as common. So this is equal to z power n into an plus an minus 1 z power minus 1 plus etc. up to a naught z power n minus 1. So to check ik is a 0, we have to get f of ik is equal to 0. But here we are getting f of ik is a non-zero number. So ik is not a 0 of f of z. So now we'll check for second option. F of z is equal to a sine 2 pi I z. We know sine function is entire function. So we'll check whether ik is a symbol 0. So first of all we check whether ik is a 0. So for that f of ik we should get to be 0. So we'll check that. So f of ik is equal to a sine 2 pi I into ik. So when we multiply this, we'll get this is equal to a sine of minus 2 pi ik. We know sine of minus theta is minus sine theta. So this is equal to a minus a sine 2 pi k. We know sine 2 n pi is equal to 0 for any n. So this is equal to 0. So we got ik is a 0 of f of z. To check whether it is a symbol 0, we have to get f dash of ik should be non-zero. I have not done that here. You have to check it for yourself. So now we'll move on to the third option. F of z is equal to b cos 2 pi into iz minus 1 by 4. Cos is an entire function. So now we'll check whether ik is a symbol 0. For that we'll check first ik is a 0 of f of z. So f of ik is equal to b cos 2 pi into ik minus 1 by 4. So when we multiply this we'll get this is equal to b cos 2 pi minus k minus 1 by 4 we know cos of minus theta is cos theta, so this is equal to b cos 2 pi k plus k plus 1 by 4. Here actually there is a mistake, so I am multiplying 2 pi inside, so this is equal to b cos 2 pi k plus pi by 2. So the value of this angle is equal to 0. So ik is a 0 of f of z. To check whether it is a symbol 0, we have to get f dash of ik to be non-zero. Here also I have not done it here, you guys have to check it, and you will get essentially it should be a symbol 0. So fourth option, f of z is equal to e power cz. We know exponential function is entire and it's never 0 for any value. So we have e power cz not equal to 0 always. So ik is not a 0. So now we'll check the correct options. So the correct options are 2 and 3. Next question, question 80. Let gamma k is equal to set of all k e power ik theta such that 0 less than or equal to theta less than or equal to 2 pi for k is equal to 1, 2, 3. Which of the following are necessarily correct? So we are given a curve here. We have to find which of the integral value is correct. So we will look into the concepts used. Singularities are obtained by equating denominator to 0. Gaussian integral formula states that if Z0 lies inside simple closed contour C, which is positively oriented, then integral over C 1 by 2 pi I f of z dz by z minus z0 is equal to f of z0 into k, where k is equal to n of C at z0. N of gamma at A is the winding number, that is the number of revolutions the closed contour gamma make around the point A in the anti-clockwise direction. So now we'll move on to the question. So they are given gamma k is equal to set of all k e per ik theta such that 0 less than or equal to theta less than or equal to 2 pi. Therefore, this implies k e per ik theta such that 0 less than or equal to k theta less than or equal to 2k pi. So, gamma 1 is equal to set of all e per I theta such that 0 less than or equal to theta less than or equal to 2 pi. So, integral over gamma 1 by 2 pi I dz by z is equal to number of revolutions, which is equal to 1. Gamma 2 is equal to 2 e raised to I 2 theta such that 0 less than or equal to 2 theta less than or equal to 4 pi, and integral over gamma 2 1 by 2 pi I dz by z is equal to number of revolutions, and here there are 2 revolutions, so this is equal to 2. Similarly, we'll get integral over gamma 3 1 by 2 pi I dz by z is equal to 3. So now we'll check the correct options. So the correct options are 2 and 4. Next question, question 81. Let f be an analytic function defined on D is equal to set of all z in C such that mod z less than 1 such that range of f is contained in C minus infinity comma 0 then. So we are given an analytic function here and the range of function is defined like this. Then we have to check which of the following option is correct. So now we'll move on to the question. So they are given f to be an analytic function defined on a unit disk and the range of f is contained in C minus infinity comma 0. So essentially the f should be an positive analytic function. So I'm taking f of z to be z square. So they have asked whether there exists an analytic function g which is the square root of f of z. So we'll check whether g of z is equal to square root of f of z. So square root of z square, which is equal to plus or minus 1. So g of z is equal to plus or minus 1 and it is an analytic function. And also g of z is equal to z implies g of z is equal to x plus iy, and real part of g of z is equal to x. Or if g of z is equal to minus z, then real part of g of z is equal to minus x. So now we'll check the correct options. First one is like saying f is necessarily a constant function. It is not so, because if you take f of z equal to z square, then range is contained in here, so it is not necessarily a constant function. So option 1 is not correct. Second one, there exists an analytic function g on D such that g of z is the square root of f of z for each z in D. Yes, because if we take g of z to be square root of f of z, it is an analytic function here, so it is correct. There exists an analytic function such that real part is greater than or equal to 0 and g of z is square root of f of z for each z in D. So we'll check that. So if you take f g of z to be z, then real part of g of z is greater than 0 and g of z is square root of f of z. So third option is also correct. By similar hypothesis, fourth option is also correct. So the correct options are 2, 3 and 4. Next question, question 83. Let f of z is equal to z plus 1 by z for z in C and z not equal to 0. Which of the following are always true? So we are given a function here. We have to check which of the following options are correct. We look into the concepts used. Singularities are obtained by equating denominator to 0. Critical points are those points z for which f dash of z is equal to 0. Function is conformal map except at its critical points. Mod z is equal to z into z bar. Real part of z is equal to z plus z bar by 2. So now we'll move on to the question. So the given f of z is equal to z plus 1 by z. So I'm taking LCM and simplifying it. So this is equal to z square plus 1 by z. So singularity is obtained by equating denominator to 0. Singularity is z is equal to 0. So f is analytic except at this point. So f is an analytic function on C minus set 0. So now I am finding the critical points. So equate f dash of z is equal to 0. So first of all we will find f dash of z. So that is equal to 1 minus 1 by z square. Simplify this. So this is equal to z square minus 1 by z square. So when we equate f dash of z is equal to 0, we will get z square minus 1 equal to 0, which implies z equal to plus or minus 1. So we know f is a conformal map except at its critical points. So f is the conformal map on C minus plus or minus 1. We know unit circle is given by mod z is equal to 1. And mod z can be written as z into z bar. So this implies 1 by z is equal to z bar. So we have f of z is equal to z by 1 by z. So in unit circle we can replace 1 by z by z bar. So we will get this is equal to z plus z bar. And we know real part of z is equal to z plus z bar by 2. Therefore z plus z by z bar is equal to 2 into real part of z. So f is mapping unit circle to a subset of real axis. So now we'll check the correct option. So the correct option is 1 and 3.